everyone, I am Queenie Claudine and for now we will going to discuss about normal distribution. See, we have definition. A random variable x is defined to be normally distributed if its density is given by f sub x of x equal to f sub x of x with the parameters mu and sigma equal to 1 over the square root of 2 pi sigma times e to the power of negative quantity of x minus mu squared over 2 sigma squared dx. So where the parameters mu and sigma squared satisfies mu greater than negative infinity but less than infinity and sigma is greater than 0. So any distribution defined by a density function given an equation above is called a normal distribution. So the symbols mu and sigma squared represents the parameters because these parameters turn out to be the mean and variance of the distribution. So we have notations of normal distribution. If the random variable x is normally distributed with mean mu and variance sigma squared, we will write it like this. So x is normally distributed with the parameters mu and sigma squared. So we will also use the notation the small phi sub mu sigma squared of x for the density and the big phi sub mu and sigma squared of x for the cumulative distribution function. So the standard normal random variable. So we can say that it is a standard normal random variable if it has a mean equal to 0 and a variance equal to 1. So the subscripts of the density and distribution function notations of a standard normal random variable is the small phi of x equal to 1 over the square root of 2 pi times e to the negative 1/2 x squared, and the big phi of x equal to the integral of small phi of u du evaluated from negative infinity to x. So since the small phi sub mu and sigma squared of x is given to be a density function, it is implied that the integral of the small phi sub mu and sigma squared of x dx evaluated from negative infinity to positive infinity is equal to 1. To satisfy ourselves that it is true, we have here the verification. So suppose that we represent the area under the curve by A, then we have A equal to 1 over the square root of 2 pi sigma times the integral of e to the power of negative quantity of x minus mu squared over 2 sigma squared dx. So and on making the substitution, we let y equal to x minus mu over sigma, and we find that dx is equal to dy. And by substitution, we get a equal to 1 over the square root of 2 pi sigma times the integral of e to the negative quantity of x minus mu squared all over 2 sigma squared dy. And we have a equal to 1 over the square root of 2 pi times the integral of e to the negative 1/2 y squared dy, since we substitute the value of y. And next, we wish to show that a is equal to 1, and it is most easily done by showing that a squared is 1, and then reasoning that a is equal to 1, since the small phi sub mu and sigma squared of x is positive, and we may put a squared is equal to 1 over the square root of 2 pi times the integral of e to the power of negative 1/2 y squared dy evaluated from negative infinity to positive infinity times 1 over the square root of 2 pi times the integral of e to the power of negative 1/2 z squared dz evaluated from negative infinity to positive infinity. then we get the product of these two equations above, and we get 1 over 2 pi times the double integral of e to the power of negative 1/2 y squared plus z squared dy dz, evaluated from negative infinity to positive infinity. And after that, by writing the product of two integrals as a double integral, in this integral, we change the variables to polar coordinates by the substitution. And we let y is equal to r sine theta and z is equal to r cos theta. And then we get that dy dz is equal to r d theta dr. So and the integral becomes a squared is equal to 1 over 2 pi times the double integral of e to the power of negative 1/2 r sine theta squared plus r cos theta squared r d theta dr. So what we will going to do is to simplify this exponent. So we get 1 over 2 pi times the double integral of e to the negative 1/2 r squared sine theta squared plus r squared times cos theta squared r d theta dr. And we will going to factor out the common in these two. Since r is the common in these two terms, then we factor it out. So we get 1 over 2 pi times the double integral of e to the negative 1/2 r squared sine theta squared plus cos theta squared r d theta dr. So by the power reducing formulas, we have sine theta squared equal to 1 minus cos 2u over 2 and cos theta squared equal to 1 plus cos 2u over 2. So what we will going to do is to substitute these values into these terms above. So then we get 1 over 2 pi times the double integral of e to the negative 1/2 r squared times 1 minus cos 2u over 2 plus 1 plus cos 2u over 2 r d theta dr. So we get, so since we can cancel it out, and we have 1/2 plus 1/2 left. So 1/2 plus 1/2 is equal to 1, and 1 times r squared and negative 1/2 is equal to, and we get is equal to a squared is equal to 1 over 2 pi times the double of the integral of r e to the negative 1/2 r squared d theta dr. Since we cancel it out and it becomes 1, and then 1, we multiply 1 into these terms. So we get this here. And then by integration, we have 1 over 2 pi times the integral of r e to the power of negative 1/2 r squared times the integral of d theta evaluated from 0 to 2 pi dr. So we get the integral of d theta, and we have 1 over 2 pi times the integral of r times e to the negative 1/2 r squared 2 pi. Since the integral of d theta evaluated from 0 to 2 pi is equal to 2 pi. So we get 2 pi dr. And we cancel this 2 pi and here, and we get the integral of r times e to the negative 1/2 r squared dr evaluated from 0 to infinity. So by integration by parts, we get negative e to the negative 1/2 r squared evaluated from 0 to infinity is equal to 1. Thus, we proved that the area under the curve is equal to 1. So thank you for listening. Once again, I am Queenie Claudine Palad, and thank you very much. God bless you.